So we've been looking at intermolecular forces. There's the big three. We've got dipole-dipole, which is between two polar molecules. We've got hydrogen bonding, which results between a hydrogen bonded to an oxygen, a nitrogen, a fluorine, and then how our kind of extreme polar ends give us this extra strong attraction that we call hydrogen bonding. And we've got our London dispersion forces, which are these kind of real weak interactions between two large nonpolar molecules. As the molecules get bigger, this attraction becomes larger and they become more and more likely to stick together. And so now we've talked about those types of intermolecular forces, we need to look at some of the properties. And so it turns out there's a real straight relationship between the properties that we start to observe on the macroscopic or on the large scale version or measurements when we start to think about our polar molecules and the way that the molecules are interacting. So it's really nice to go, okay, molecules polar, here's what we see. It explains these properties that we see. And so kind of, you'll notice I've grouped them kind of into two different categories here. Some of these you probably recognize. Boiling point, melting point, excuse me. Boiling point is the temperature at which our liquid molecules turn into a gas or vaporize. Now, if we were to think about this, well, what's holding those molecules in the liquid phase? That would be the intermolecular forces. And so if they have high attractions, the higher the attractions in our liquid phase, the more energy you'd have to put in to get it to boil. So there's a direct relationship between our intermolecular forces and the temperature at which it takes to boil. The higher the boiling point, the stronger the forces. Cool, melting point. That's, the temperature it takes to melt something. So, same deal. The stronger your attractions, the hotter or warmer you have to, more thermal energy you have to put in to get the solid to break apart, break away from one another to turn into their liquid phase. So again, a direct relationship between the higher the attractions, the higher the melting point becomes. Surface tension, we're familiar with this from water, but this would be for any liquid. We've got kind of an attraction between the molecules as we think about kind of this kind of a repulsion or this film, if you will. Surface tension is describing how tightly those liquid molecules are attracted to one another at the surface of a substance. Surface tension, if we were to think about it, if the attractions are higher, surface tension would also be higher. We would see another direct relationship there. So surface tension, attraction to one another at the surface of our substance. The one that's probably new here is viscosity, and this is your resistance to flow. The resistance to flow. Sorry, I should have done this at the beginning because it's going to be pretty underwhelming here. So here we've got just some water. This is liquid water, and so we will notice that if we just kind of turn it, it pretty readily it flows. It's got a pretty low viscosity that does not resist flow very much. If we look at our vegetable oil, pretty similar, but we could measure it is actually a little more viscous, has a slightly higher resistance to flowing. And then we've got some Caro syrup here, right? Some Hy-Vee brand light corn syrup. I should have flipped this at the very beginning because I can turn this full upside down. And we might get lucky and see a slight bow or a slight drip. Yeah, no. If you're interested, it's called the pitch experiment. It's one of the longest running scientific experiments that we are still ongoing. It's the pitch drop experiment run out of, I think it's Australia, that we've got these folks that are measuring how long it takes for tar or pitch to actually drip into a beaker. And I think we're on the 14th drop, and it's been going for 200 years. Check it out. There's a live stream if you're really looking for stuff. You can notice, it's starting to go. Yeah. So we said this has a fairly high viscosity, a high resistance to flow. Oh, it's starting to go. Look at it go. And so if we think about it, viscosity is also a direct relationship. If you had to compare the attractions between our Caro syrup versus our attraction in liquid water, these attractions are less, so it flows easier than our corn syrup. And so viscosity is also a direct relationship. These are all directly related. Spelling. Directly related to our intermolecular forces. The stronger the forces, the higher all of these values become. The higher the attraction, the slower it is, or the higher the resistance to flowing. The higher the attraction, the higher the surface tension. The higher the attraction, the higher the melting point, higher the boiling point. So these are all direct relationships to what we see in our intermolecular forces. So we can actually see how these molecules are starting to interact even on the large scale. Vapor pressure is new. Vapor pressure is the pressure exerted by particles in a closed system. What do I mean by that? So if I had a flask, you'll have to pardon my artistic ability. If I had a flask, a sealed flask, so I'm going to put a rubber stopper in here. Rubber stopper, sealed up. If this was a flask and it was sealed, and in that flask I had already put in there, obviously I would have had to do this before I sealed it up, but say I had put in a liquid. Let's say, just for sake of arguments, let's say it was water. Cool, so water, if we're thinking about water, that's going to have hydrogen bonding, so fairly high attraction. But we know that water, over time, if I just spill water on the floor, some of the particles, again, this is a numbers game, billions and billions and billions and billions of particles, all at slightly different speeds. We measure the temperature as the average kinetic energy, but some of them are going really slow, some are going really fast, and some of those ones that are going fast enough are going to break free from the liquid and evaporate. You know this to happen. Puddles evaporate over time. And it's not that the puddle ever got to 100 degrees, it's that enough of the particles happen to get enough of that energy to escape from the surface of the water. And we call this the vapor pressure. Vapor pressure is the pressure exerted by some of these water molecules splitting off and escaping into our chamber. And this just happens. This is a process that happens anytime we have a liquid and we put it in a sealed container. Some of the particles escape. And this pressure we can measure, we call it the vapor pressure. Now eventually you'll reach a point where enough water particles have escaped that if another one escapes, another one pops into the water. We call that equilibrium, where we technically it's still changing, but they kind of cancel each other out because as one leaves, another enters. And so we reach a point where this vapor pressure remains kind of stagnant, where we've gotten as much above the liquid as we can get before we reach equilibrium. So that's what we call our vapor pressure. If we had another flask, for example, and say we had, throw back to our hexane, C6H14. Well, this is a nonpolar molecule. If you remember, this was that long hydrocarbon nonpolar. There's some LDF that holds it as liquid, but LDF is pretty weak. It's the weakest of the intermolecular forces. So as a result, this starts to escape pretty readily, and so we would end up with much, much more above the surface. And so we would say we had a larger vapor pressure. And so you'll notice why we split these into two groups. These are all direct relationships. As the attractions increase, all of these values increase as well. But for our vapor pressure, if you have more attraction in the liquid, less of the particles get to escape. Less of the particles actually escape. And so it's an inverse relationship. Inverse relationship. As the attractions go up, the vapor pressure goes down. And so we can start to think about what our intermolecular forces will do as we have our different substances. And I didn't do a good job of this in the previous video, I apologize, but if we're thinking about our strength, in terms of our intermolecular forces, London dispersion forces, very much the weakest. They are the easiest to split apart. They have the lowest boiling temperature. They have the highest vapor pressure. Right in the middle, we have our dipole-dipole, where we got two polar molecules. They've got a fairly strong attraction. They're going to have slightly more attraction than our LDF. And then hydrogen bonding, that's a reason it's a special class. Hydrogen bonding is our strongest of our intermolecular forces. So that's why water boils at such a high temperature, 100 degrees Celsius, even though it's just one oxygen and two little hydrogens. You'd think it'd be pretty easy to get that water to break apart. These hydrogen bonds really stick our water molecules real close to one another. So we can start to see this relationship between the particles and the way they're built, polar, nonpolar, and the relationship to these properties that we see when we start to interact them with one another. Cool. Just some of the properties as we start to think about it as we look at our intermolecular forces.